Welcome to the ITC 2021 Diamond Supporter presentation brought to you by Tessent and Siemens EDA. In this session, we are going to share 4 presentations with you. Joe Sawicki and Janusz Rajski will speak about our commitment to innovation. Mark Kassab will talk about what he and his team have been up to since the streaming scan network technology was launched at ITC 2020. Then, 2 of our partners will talk about their experience with the SSN technology, Srinu Alampally of Broadcom and Dehnert of Intel. Feel free to ask questions in the chat window during the presentations. We will have a Q&A session with the presenters live at the very end of the presentation. First, I would like to introduce the Vice President of IC EDA, Joe Sawicki, and the Vice President of Engineering, Janusz Rajski.
Here in the Siemens IC EDA segment, we're focused on enabling our customers to be able to design smarter systems faster through focusing on 3 main axes. First is on process scaling, whether that be on new technology nodes or 3D integration. Secondly, on design scaling, enabling our customers to take advantage of this increased capability presented by these new processes in a very effective manner. And finally, on system scaling, looking at how we can do validation not just of individual elements on chips themselves, but complete systems pulling together both software, hardware, and the mechanical and analog interfaces into the real-world environment.
The aspect that impacts DFT the most and most directly is design scaling. Just the sheer size of designs actually breaks the tools and flows that are currently used. So companies use ad hoc solutions which are not very productive in terms of the time that it takes to insert DFT, but they also pose schedule risk and very often produce suboptimal results. So it is very clear that we're at a point that a new SoC-level DFT methodology is needed to address those needs in a fully automated and scalable manner. And we have to admit that so far, we didn't have SoC-level DFT. In order to cope with the enormous complexity of SoCs, the solution has to be hierarchical. The other requirement is that the data throughout the chip to many cores has to be delivered through high-speed test bus, or actually even better through streaming mechanism that optimizes bandwidth utilization. If you like all these requirements, the good thing is that we already have a solution which is called streaming scan network. So now you might ask a question, do I really need it? If you're not using it already. Well, I assume that you design SoCs, and SoCs will get bigger and bigger with time. There will be more cores. The time pressure will be even more, so you will need to reduce design cycle just to address competitive pressures. Your team will not be bigger. So if you're not using hierarchical DFT, then your solution will be suboptimal. If you're not using SSN, then you will spend more time on designing DFT, inserting, planning DFT than it is necessary.
We're also breaking new ground and putting together new connections with the rest of the ecosystems by extending our Tessent platform into the silicon lifecycle. We pioneered this in 2018 with Tessent Mission Mode, set up to do validation that his chip is still structurally correct while being operated within a system. In 2020, we strengthened this portfolio with the acquisition of Ultrasoc, bringing our ability now to manage not only looking at the structural viability of a chip, but also looking at the functional correctness with on-chip monitors that tie into this as an overall architecture. These silicon lifecycle solutions will be a game changer for the industry in terms of being able to monitor power, performance, reliability, security, all throughout the product's overall life cycle. SLS Tools is going to help companies with faster time to market, instant error correction, preventative maintenance, and managing recalls. But it's also going to provide a feedback loop that will enable customers to design better products, manufacture better products, and increase ROI across the lifetime of ICs. And last but not least, I'd note that Siemens EDA has been a pioneer in leveraging machine learning to increase the effectiveness of our tools. In 2009, we introduced machine learning into our Tessent Yield Insight product to analyze production fail data to find significant systematic yield failures in production of ICs. And this has had a major impact in terms of people's ability to deliver at high yield rates while finding those difficult to find bugs in the production process. At Siemens EDA, we're dedicated to delivering more test innovations to you to help you engineer a smarter future faster. Thank you.
Mark Kassab is the Senior Engineering Director of the ATPG and Compression Products at Siemens EDA. He received his PhD degree in electrical engineering from McGill University, Canada in 1996 and subsequently joined the Design for Test group at Mental Graphics. Mark is a co-inventor of several test technologies, including the embedded deterministic test and streaming scan network technologies, and is the original lead developer and architect of Test Compress and a co-designer of the Tessent platform.
Hello everyone. Last year at ITC, we, along with our partners, introduced Streaming Scan Network as the next generation hierarchical test solution. The key benefits it provides are the ability to cut your DFT planning and implementation time in half, as well as to reduce your test time by up to 4x, or sometimes even more. Since then, we have seen tremendous interest and fast adoption. We now have 6 designs in silicon and many others in flight, including 6 that are expected to tape out before the end of the year. Many of our customers have deployed or are in the process of deploying SSN, including all of our 5 top customers. You'll be hearing about some of those experiences later in the session, as well as in our booth. Let's start with a recap of what SSN looks like and the benefits that it provides. SSN consists of a synchronous parallel bus that delivers packetized scan data from one core to the next. Each core has the same plug-and-play interface regardless of the DFT within or the size of the core, and regardless of the number of cores within the design. Within each core, there is typically at least one scan host that interfaces with your EDT compression logic and/or your uncompressed scan chains. As the data flows through the cores, each scan host reads the data that's destined for it and performs one shift operation when it has enough data to perform one internal shift. The scan host generates all DFT signals locally, so it knows when to shift, when to transition scan enable to 0 in preparation for capture, how long to wait for scan enable to propagate, when to perform capture, and so on. For efficiency, we only stream scan data through the bus. The scan hosts are programmed during setup using IJTAG to follow the protocol and track when to perform each operation without being explicitly told to do so. This results in 100% payload efficiency, and all of this setup is completely automated. Because all of the scan signals are generated locally and all of the chains terminate within the core, timing closure is greatly simplified. So in fact, no scan signals cross the core boundaries except for the SSN bus. And the SSN bus has nodes you can use, such as FIFOs, that allow you to tolerate arbitrary clock skew between cores without slowing down the shift speed and without having to balance the SSN clock globally throughout your chip. I do want to point out that this is a highly simplified picture, which doesn't represent everything that you can do. Like IJTAG, the SSN network is configurable, such that you can include or exclude different portions of the design. And if it makes sense for your physical design, you can implement multiple buses or data paths and operate them concurrently if you want. The first set of benefits relate to reduced test planning and implementation. A key benefit is that SSN decouples core and chip-level DFT. This means you can optimize scan and compression configurations of each core without worrying about the rest of the chip or about the number of top-level IOs available at the chip level. So in fact, you can drive any number of cores with any compression configurations using a bus of any size, and it could be down to a single bit. And the bus width is actually scalable. So you can choose, for example, to implement and operate the 32-bit bus at package, but scale it down to 1 or 2 bits at wafer test. You don't have to decide at implementation time which cores you want to test concurrently. You can test one core at a time or as many cores concurrently as you want, and decide this at pattern retargeting time with no changes to the hardware. So as I mentioned, the only scan signals traversing the core are the parallel SSN bus and its clock. The cores have a fixed footprint, and this architecture is ideal for tiling with abutment, where the bus output of one core feeds into the bus input of the next core. This simplifies routing as well as time enclosure. The other set of benefits relate to test time and test data volume reduction. If you're driving multiple cores in parallel and your internal chains are limited to 100 MHz, for example, you can easily run the SSN bus at 200 MHz or more. So that right there can give you about 2x reduction in test time over driving the scan directly from the IOs. And as I mentioned earlier, each core can be optimized independently to minimize its test data volume. Then when you retarget and merge the patterns, SSN can automatically balance the bandwidth between the cores to reduce padding, which is otherwise known as white space. If you have identical cores, you can get significant incremental benefit because you can test any number of identical cores in constant time and with constant amount of data. We take advantage of the fact that both inputs and expected values are identical for every instance, and do so while still enabling you to collect data for diagnosis with the same pattern set. Now let's go back to the three axes that Joe and Janusz talked about: technology scaling, design scaling, and system scaling. In the context of test, SSN as presented primarily targeted design scaling by reducing implementation cost and test cost for SoCs. But beyond those benefits, and as we look at some of the other upcoming needs that stem from design system scaling, we see that SSN plays a pivotal role by providing essential infrastructure needed to meet those requirements. Let's take a brief look at the three highlighted areas: multi-die designs, leveraging high-speed IOs for test, and high quality in system test. And let's see how SSN is a key piece of each of those solutions. If you look at test access challenges in multi-die packages such as 3D designs, you basically have tiling on steroids. You need dies to be testable on their own as well as in a stack. Your test access mechanisms need to be able to send data up and down the stack and select which die or dies are tested in a given session and which are bypassed. The IEEE 1838 standard describes how to do this for both JTAG as well as scan test. On the left side of the picture, the primary and secondary tabs on each die provide access to the die as well as dies above and below. This can all be modeled in ICL and is supported natively using iJTAG. On the right side of the picture, the flexible parallel port, or FPP, is a parallel bus that provides the scan data. It needs to have the same access flexibility as we described for the JTAG side. SSN is ideally suited to implement the FPP scan access mechanism since it provides data over parallel bus, which can be reconfigured, which can drive any number of cores, and because it generates all signals needed for scan test locally. And just as with cores in a tiled design, with the same interface on every die, you can send data up and down the stack and access one or all dies concurrently through the same interface. The second application to look at is reuse of high-speed IOs for test delivery. There are two design trends that are compounding to increase your test time. As dies are getting larger and require more data to test, there are often fewer GPIOs available for scan access. It's increasingly difficult to reuse high-speed SerDes IOs as single-ended scan pins without interfering with their functional mode. Additionally, multi-die packages are also limiting accessibility since all test data for the stack has to come through the bottom die and its IOs, as we saw on the previous slide. To keep test time low in large pin-limited SoCs, and especially in multi-die packages, using high-speed SerDes to deliver scan data at multi-gigabit per second per lane can provide very high bandwidth solution to get test data quickly on and off the chip. And this is what the IEEE 1149.10 standard enables you to do. The PEDA IP, which is part of the standard, reuses your functional PHYs and streams scan data internally on a synchronous parallel bus. This interface exactly matches the SSN data path, which can then connect to the PEDA and take care of fast on-chip distribution of test data. The SSN bus in this case can easily operate at 400 MHz. SSN also takes care of local generation of test signals such as scan enable and shift clocks with the right programmable timing, which is an often overlooked challenge. The final application we will look at is in-system test. It's well known that increasingly ubiquitous automotive and server ICs have in-system test requirements for safety and reliability reasons. This has traditionally been done with solutions like BIST that require little or no external data. However, we see increasing interest in two areas. First is achieving even higher test quality than possible with random patterns. Second is increased X tolerance. Both of those objectives are feasible if you have an environment that is capable of delivering deterministic test data during in-system test. And remember that especially in automotive applications, you have a very short time interval in which to do so test time is critical. On the previous slide, we saw how during manufacturing test, the high-speed SerDes and PEDA can interface with SSN for fast test delivery and in-core generation of test signals. An almost identical configuration is possible here during in-system test. However, instead of the SSN being connected to the PEDA, it's connected to an internal CPU interface to which you can write scan data and either check the pass-fail information at the end of the test or unload scan data as you go, especially if you want to collect captured data for diagnosis. So to wrap up, I want to leave you with two key points. The industry is adopting SSN very rapidly in the transition to packetized scan data and gaining benefits in both DFT implementation productivity gains as well as in reduced test cost. Secondly, beyond those immediate gains, SSN is foundational to meeting your future SoC DFT requirements. Getting SSN into your flow today gets you one major step closer towards being ready for tomorrow's needs. Thank you for your attention.
Srinu Alampally is a master engineer at Broadcom, where he focuses on high-speed design DFT and coordinates internal DFT forums in Broadcom. After post-graduation in microelectronics from IIT Bombay, he worked at Texas Instruments before the current job. His main interest is in low-power test, high-speed designs, and reducing test cost. Srinu co-authored multiple technical papers and is co-inventor in 3 US patents.
Hi, today I'm going to talk about how we used SSN to enhance test on one of the 3 GHz designs, and we also show how we can scale it for other designs. We are part of a Broadcom central engineering team, and specifically our group designs just CPUs. We provide the CPU, hardened CPU macros to the rest of the Broadcom business units. On average, we do 20 to 26 designs, and with varying complexity, multiple voltage domains, multiple power domains, and some of them are very, very targeted for very, very low power applications, and some of them are targeted for very high frequency or high performance applications. They are typically instantiated multiple times, anywhere from 2 times to 30 to 64 times. Our team is always at the forefront of adapting new technologies to solve, as long as we see that it helps in solving design challenge. We name it shared bus memory based and IJTAG, and even SSN. We started designing a production chip with SSN as early as 2019. This presentation talks about how we used SSN to solve some of the design challenges. The CPUs, especially the high performance ones, tend to have significant portion of the power in dynamic power. And to reduce the dynamic power during the test, we tend to use the low power options that results also in higher pattern count compared to a similarly sized non-CPU design. The ideal way of testing this homogeneous multi-core is to test all of them together to make use of the input stimuli is shared for all these cores. But typically we end up not having enough IO bandwidth, and also the test power is another significant challenge. So to test all cores is, if not possible, we try to target multiple cores, and that experiment of how many cores we test most of the times is done post silicon. And one of the challenges is that due to the pre-silicon decisions that are made, some of these combinations might not be even possible to try. The other thing is to delay the capture across these cores to improve the test power, to reduce the peak capture power, but it's not scalable and it's not systematic, and it also increases the test time. There are several benefits with SSN. I'm going to just talk about how the benefits that are directly applicable for these multi-core high-frequency blocks. The first one is the on-chip compare, where in addition to the scanning data, the expect and the mask data is sent on the SSN bus, and the SSN the comparison with the comparison is made on chip at the IP level, and there is also a status bus that gets sent out on the SSN bus, where the comparison can be made on ADE or the IJTAG sticky bits, which capture the overall test status that can be used at the end of the test. As long as the core is instantiated more than 3 times, you would see a benefit with this approach. The other benefit is because SSN is packet based and all the control signals are generated internally that are required for EDT. So the capture and the shift for each of these IPs that are tested with SSN are not aligned. And that actually reduces the burden on the power rails to support the capture during the capture. So the side benefit is you could actually, even though you're testing all the cores together, but the peak capture event is not happening at the same time for all these cores. So as you can see in this picture, they are staggered. The capture event for all these cores is staggered across the time. There are other benefits with SSN, like the EDT configuration can be freely chosen, and also JTAG can be used for debug, but I'm not going to go into the details of it in the interest of time. The challenges in adapting SSN for many of the designs is a major methodology shift compared to EDT, and there's a lot of learning required. The other thing is the area. SSN takes up additional area compared to the EDT. It can vary from 20% of the EDT area to as high as the total EDT area, depending upon the SSN options and the SSN bus width. The SSN adds additional logic, so there are STA considerations need to be made, and they need to be timed. The buses need to be timed, and the SSN uses EKIL for modeling all the SSN buses and the SSN logic. And so the EKIL extraction also tends to be more complex than just having a traditional EDT. So to address these challenges, a lot of designers have chosen using a test chip as a vehicle, and then develop a flow and then deploy it on a production chip. We actually used an alternate approach where we use SSN sparingly on very high impact blocks and fine-tune the SSN bus weights and collect the data post silicon, and then over time increase the SSN on the other IPs. Since SSN is implemented on a partial design, we wanted to keep the flow impact for the SOC level and the other IPs as minimal as possible. So there are 2 TSDBs delivered to the SOC, one without SSN, where the SSN and SSN is removed from the EKIL and the TCD files and delivered to the SOC. Just the SOC level connections required for SSN are made manually. And the patterns are retargeted and delivered to ETE. With SSN, the original EKIL and TCD files are used, and EKIL is re-extracted at the SOC level, and patterns are retargeted at the SOC level and delivered to AD. Here we talk about how we implemented and what are the benefits of our implementation at the SOC level. As you can see here, there are two levels of hierarchy. There's a block level, which is instantiated 12 times, and there's at the SOC level, where all these EDTs are clubbed together and sent out to connected to using the pipelines. With SSN, the connections are made manually at the SOC level, reusing some of the EDT pipelines for SSN. And because this logic is not added using the DFT spec, the EKIL for them needs to be modeled manually, and then we extract the EKIL and then generate the patterns at the SOC level. This is if there are three levels of hierarchy: a block level, a parent block level, and the SOC level. The block level has the EDT and SSN, but the parent block has just the EDT. And the connections here represents the EDT connections, and also the pipelines are for the EDT. For the SSN, all these pipelines are reused that were originally inserted for EDT, and the connections for SSN are limited to just the parent block, and the manually we need to model EKIL for all the pipelines that are reused for SSN, and then that SOC level EKIL is generated. Here we talk about how we used SSN on a design where there are 12 CPUs of a homogeneous instantiated 12 times, and there is 16 input bus width and 4 EDT output are used, and because there each CPU is instantiated 12 times, so there are 48 outputs and 16 inputs, so that make up 64 total IOs used for EDT. And for SSN, just the 16 inputs and 16 outputs, and the comparison is made just on the IJTAG status bit during the SSN. And this is a very high frequency design, spec'd for more than 2.5 gigahertz. Because we are using on-chip compare, even the test time also is lesser than EDT. Here we show the Shmoo plot post-silicon that is obtained when we test all the 12 cores together. On the x-axis is the frequency and the y-axis is the voltage. The pass is represented with the green color, and the fail voltage condition is represented with the red color. You could see that there is a 30 millivolts difference between running 12 cores at a time with EDT versus 12 cores running with SSN. Actually, with SSN, when we tested 1 core versus 12, there was no difference in the Shmoo plot, whereas with EDT, the Shmoo degraded by 30 millivolts. So that actually says that this approach is pretty scalable with SSN when testing multiple cores, because the peak capture event is not happening at the same time, versus with EDT, all the capture events are all the peak power capture events are happening at the similar time or the same time. Here the Shmoo plots, again Shmoo plots with the shift frequency versus the voltage of operation. The x-axis is the shift frequency and the y-axis is the voltage. There are no cycle-to-cycle comparisons again, even for this Shmoo plot, and all the 12 cores are run simultaneously, and the IP is timing closed for 150 megahertz shift. So as you could see, around 75 megahertz on when we run with EDT, the design started failing. Whereas with SSN, we were able to actually run beyond 75 megahertz and up to around closer to 150 megahertz. So there is an improvement in the shift frequency close to 2x versus EDT. To summarize, when we were asked to implement a scalable test solution for very multi-core high-speed CPUs, we are actually able to show how we can adopt SSN with the least disruption and showed benefits with the post-silicon data.
Dave Dehnert is a principal engineer in the device development group at Intel, where he works on client CPUs. He grew up in upstate NY and graduated from Cornell University with a BS in electrical engineering and Masters in operations research and industrial engineering. He joined Intel in 1995 and has, over the last 18 years, worked on every area of scan, from architecture, RTL, and validation through SD, timing, ATPG pattern generation, all the way to SI debug, content enabling, and low-yield analysis.
I'm Dave Dehnert. I'm the scan lead at Intel's device development group, which is the Oregon-based client design team. We recently launched Tiger Lake, which is currently in the marketplace, and are now working on the next generation client designs to be launched in the near future. Last year at ITC, Glenn presented an evaluation of SSN compared to one of our custom test fabrics, and today I'm going to present an actual implementation. I'm going to start with an overview of the product and then share the SSN implementation details. I'll then talk through some thoughts on our experience implementing it, as well as retargeting, before sharing some retargeting data. One of our upcoming products that implements SSN is a multi-die product consisting of 4 die. As you can see in the diagram, SSN's been implemented on 2 of the 4. The other 2 each have a different custom test fabric. The nice thing about this implementation is that it allows us to phase in SSN as we slowly replace some of our legacy test fabrics. You'll also notice that they were using different SSN buses and we're sharing the same IOs between the custom test fabrics and SSN. This implementation gives us a lot of flexibility, allows us to phase in SSN over time, and it also allows us to keep using high-speed test fabric with limited test IOs. Let's take a closer look at the SSN implementation in Die 3. We have an SSN bus width of 48 bits and a bus clock frequency of 400 megahertz. The scan clock shift frequency ranges from 100 to 200 megahertz. As far as the components, there is 139 SSN hosts, and the host is the interface between the fabric bus and the EDTs. We use 61 S pipes and 31 R pipes. These are basically repeaters to meet timing. There are 10 S muxes and 8 DSKU FIFOs. The fabric itself is divided into 7 subrings that I'll go into more detail on in the next slide. The SSN fabric is implemented hierarchically with 7 subrings that match the functional subhierarchies in the design. Using the subrings along with corresponding DSKU FIFOs allows the clock within each subring to be balanced separately, and it improves the fabric timing. Each host is connected to one or more EDTs and separated by the necessary repeaters. One thing that we found useful was using the SMUX for other non-scan custom features that used to share the same test fabric. In scan mode, these are obviously just bypassed, and when we're using the other feature, all the other SMUXs and hosts are put in the bypass mode, and we just reuse the flop repeaters. The implementation of the fabric was fairly straightforward. Planning of the network, the location of the hosts, the number of flop repeaters and location of flop repeaters along the path, and the dividing it up into subrings was pretty much the same as what we're used to with our own custom test fabrics. The creation of the network was very simple, very similar to creation of EDTs or any other DFT logic with Tessent. Probably the one place we struggled a little bit was with the ICL, PDL, and TCD, as there's an initial learning curve required and some upfront effort to enable. We weren't able to fully annotate or implement all of our legacy taps with ICL and PDL, so that we do still have some customization or hacks in there. But we found the ICL extract to be a very efficient form of validation, and we use it often. One other thing that we did note was some of the retargeting parameter ranges are limited to the register size that's set during creation. So there's a little bit of a learning curve there. For example, the number of wait states between, say, shift and capture is limited by the register size, and we find some really slow clocks. We had to go back and tune that. Now let's switch gears to retargeting. Initially, we had some difficulty getting the design elaborated with our early netlist, where ports would mismatch and we didn't have all the collateral necessary to get the retargeting to work. Once we did, we found the hierarchical retargeting very useful. We do it at the subsystem level first, validate everything there, and then retarget one level up, and then sometimes a level up beyond that. This is great for very large designs. We also found it useful to be able to run ATBG without the host present. Initially, we weren't sure if this would work or not, but we often have the EDT in a different design block than the host, and we found that works without any problem. Looking across the entire die, for the large pattern sets, the efficiency gains are very effective. However, we have found that with small pattern sets, it's less efficient, or perhaps our fabric or our implementation is a little too big for what's needed. We are, with our older custom fabrics, we're used to having more direct control over some things like the bus frequency, where we like to keep it fixed at one frequency, regardless of what it is. And what we found is that if the pattern is smaller with a slower frequency because we didn't fill the bus up, then it'll switch the frequency to be lower. Another concern that we had was the ability to find a failing partition or the failing block, since it's packet based. But all of the information needed to calculate which block is failing is all right in the style, and it was pretty straightforward to implement something to satisfy those requirements for our manufacturing flows. And now the big reveal, the retargeting data. What we have here is on the table, in the table on the right is the ATBG data for all the blocks within one subsystem. One thing to note here is that some of these are instantiated multiple times, and I've only included one instance in the table to make it readable. So some raw statistics here. The total number of tester cycles is 2 million, or roughly 2.7 million. The retargeting runtime was 1 hour and 18 minutes, and 91% of this pattern was parallel data, meaning the parallel SSN fabric or bus traffic. The rest of it was the tap configuration at the beginning, something that we were also a little worried might be large. What you can, so I was trying to find a good way to illustrate the efficiency. We couldn't really, in this case, compare it to our older fabrics because we don't have them implemented, and it would have been a lot of work. And then Peter, who works with me, actually went through and came up with this graph. He sort of calculated the same throttling data that was in some of the training foils. So what you can see on the left is this is the data if it was just shifted in raw, and all of for each one of these bars, the data below the red line would essentially be wasted space on the tester. And on the right, this is after it's been retargeted and the partition is throttled to try to reduce all of that wasted space. You can see that it's done a great job. For all of the patterns or all the blocks with a large amount of data, they're very, very efficient. The ones that stick out, which I've highlighted on the table, are the ones that have very small pattern counts, and it can't possibly be stretched up to that line unless perhaps in the future they're stacked on top of each other. So to sum things up, SSN is very flexible. It can be phased into a design. The implementation is straightforward, no difficulty converging the design. The retargeting works as expected. We haven't tried any of the advanced features yet, but we're looking forward to it. And the efficiency gains are in line with our expectations of using a narrow, high-speed test interface. Thank you.
We would like to thank Mark, Shmoo and Dave for their presentations. We invite you to join us in the technical sessions here at ITC. In particular, we suggest special session 1C on 3D on Tuesday at 9:30 a.m. PDT, 3DIC test challenges, trends and solutions, an EDA perspective. Session 4C on Wednesday at noon on reduction of deterministic test pattern sets. Session 4D, also Wednesday noon, embedded tutorial on memory testing, including sections on MBIST requirements, memory repair, and EMRAM test challenges and MBIST support. In the ITC Lounge, look for the Siemens logo to find our 4 booths. In the Tessent DFT booth, you can learn about the brand new ATPG Boost and other recent additions to our DFT product family. In the Tessent Operations booth, you can learn about the latest in statistical diagnosis and silicon bring-up. Visit our Beyond Test booth to learn about our silicon lifecycle offering and solutions for the automotive industry, safety and cybersecurity. And last but not least, visit our theatre to attend live presentations from Tessent experts and industry partners, including ARM, Broadcom and more. We have presentations during most breaks in the ITC technical programme. The theatre schedule is posted in the booth. Thank you for joining us today. We will now open the floor for questions.
Okay, thank you all for joining us. And we have, as you can see, Mark, Srinu, and Dave with us to be able to answer some of the questions. I know Mark was overeager and started answering some of these in the chat already. But Mark, one question that came in early was from Pradeep Kapoor. He asked, how can we achieve the staggered shift and capture in SSN? What happens for the interface faults between the cores?
All right, so there's two parts to this. When we are retargeting patterns that were generated for each core out of context, then the cores operate completely independently, because shift and capture and scan enable are all generated local to each core. So each core works completely independently, and one core might be shifting while another one is capturing. Obviously, in that mode, you're not testing interface between different cores. In external test mode, when you run ATPG on multiple cores and you are targeting faults between the cores, then the nodes are programmed so that they can shift independently for one scan load, but then they coordinate capture. So we wait until they're all done shifting, and we allow them to capture at the same time, so that capture looks the same for the ATPG session, whether you're using SSN or direct access.
Okay, thanks, Mark. So we did get I guess a question here that just came in from Arvind Jain. I'm taking these questions in random order just because that's how I feel like it. So Arvind asks a question that he asks to both, I guess both Srinu and Dave can try to answer, which is whether you, I'll let Srinu answer first, whether SSN was inserted at in RTL or in the netlist. And I'll let both Srinu and then Dave comment on your flows.
We did insert as a part of EDT, so it's a netlist insertion.
Okay, Dave, how about you?
On our side, we implement SSN and EDT in the RTL.
Okay, thanks, Dave and Srinu. And another question that I think you all might have some answers to, and I'll let Srinu and Dave answer in that order as well, was the impact on test time. There was a question here from Jadiv Shenoy, and I apologize if I mispronounce her name. The question is, what is the test time impact? So even though the shift frequency is higher, the packets are now delivered serially. So we have to look at the final test time. Any comparison there?
Yeah, let me address that first. So if you look at in my design, the EDT input bus width and the SSN bus width are actually same. So there is no test time impact with SSN, even though it is serially sent. It's just pipelined. It is not like it is one after another. So there is no test time impact if they were run at the same frequency. Now that we could run all these cores, at a 2x the shift frequency compared to the EDT, so that test time actually reduced by half. And just to answer further, I mean, it depends upon what they choose the SSN bus width as. So it is design dependent. But SSN itself, I mean, we shouldn't think it as a serial. It rather is a pipelined packet based.
Thanks, Srinu. And Dave, do you want to see or comment on how you experienced it?
Yeah. So from my perspective, we have a parallel bus with an I/O connected to the tester that runs at a specific frequency, and that is the limit to our test time. So our goal is to make sure that every bit that we shift in is a useful bit of information. And therefore, if you have 0 wasted bits, you have the fastest or most optimal test time that you could possibly have. And reducing the unused bits is what SSN is good at, or the advantage that we take from it.
Okay, thanks, Dave. So Mark, I have a question I'll send your way. that is, how do you typically would you handle failure analysis for scan data, as SSN has very large amounts of data, and SSN, so is SSN limited to production testing only when yield is high, or how do you tackle data collection?
Yeah, so I wouldn't say that SSN data is high. SSN data is actually the same as non-SSN data, but you have the ability to morph it to whatever interface you have. Anything that you really can do with direct access, you can do with SSN. All you have is basically a more complex transformation network. So you don't have a direct wire from the core level channels to the top. You go through this network. But aside from that, any data can be delivered to the cores and out of the cores. So really, any FA that you can do directly, you can do with SSN, and you have complete control on how many cores you're testing at a given time. If you want to go debug one design at once.
Thanks, Mark. So I have actually a couple of questions that are very similar for Dave. The question from Dan Trock and also from Samir Bubazari, and both of them ask about timing. And Dave mentioned that timing analysis was easy. Can you comment on challenges closing timing? And I think also Samir says, any challenges facing closing timing for the SSN clock traversing all the cores and subsystems?
So, I'll preface this with saying that prior to SSN, we had our own custom test fabric that was, from a convergence standpoint, I'll say somewhat similar. But regardless, you need whether you're just going to connect scan chains directly to the tester, you do have a clock and a bus that's going to go all around the die. So there's really no difference there. What SSN gives you is the opportunity to make it go faster, to maybe have a narrower, faster, more configurable bus. It's really, there's nothing special about it. You can add as many flop repeaters as needed along the path. So, with very basic planning, you can figure out how many you need and put them in. And, if you have too many, you can remove them later. And then, as I said in my presentation, having the muxes and deskew buffers allow you to take portions of the die and sort of balance the clock and converge it separately. So there's some nice features in there that make it easy, assuming you know how to do basic timing convergence.
Thanks, Dave. So I have a this is a question, I guess, for, well, I'll send this question towards Srinu. That's brought up by Sagar Sabade. And can you comment on the learning curve with SSN? Any impact on the chip level architecture or flow?
Yeah, it's a pretty complex question. I mean, it depends upon the number of voltage domains, power domains that you have, and there's a lot of planning required for SSN so that the buses don't get dropped off, right? So yeah, there's quite a bit of planning required ahead of the ahead very early in the game. Dave, I think, is the best person to answer this question rather than me, because we actually implemented only on part of the design.
Okay, Dave, I'll send it back to you. And while I do that, I'll also pitch our theater in our booth, because we do actually have some sessions on different aspects of SSN that might also help some questions people have about learning curve. But Dave, I'll let you answer this one, and then I think that's the last one we're going to have time for today.
Sure. I alluded to a little bit from the designing standpoint, since we're used to this type of thing. That was pretty straightforward. It's the getting ICL extracted all the way through, and sort of having that play nicely with some of our non-standard tap and other type of implementations. That was sort of the learning curve. So it was more on that side of things, and not really on the design or using the tool side of things.
Okay, thanks, Dave. So I think we're pretty much at the top of the hour here, so I think it's time to wrap up. There were some questions that we weren't able to answer. Feel free to